Good day, students. My name is Shehu Sanusi Lalin. I'm one of the course lecturer for this particular course, Maths 121. That's the course title and the course code. And the title of the course is Elementary Mathematics. Some of the topics you are going to learn in this course include limit and continuity of a function, differentiation of a function, integration of a function, and so on and so forth. With me taking the course are 5 other lecturers which will come with their own segment. So for this segment, we are going to be looking at the limit of a function, left and right hand limit, L'Hopital's rule on limits, continuous function, and then finally we round up with exercise for the first week. Now, what is a function? Let X be the set of numbers in a set X and Y be the set of numbers in a set Y. Then the rule which assigns each element of X to each element of Y is called a function. And we write Y equals to f of x. The set X is the domain of function f, and the set of values of Y is the range of function f. F of x is called the image of x under the mapping f. Function f is said to map an element of x into an element of y. Now, what is the limit of a function? If a function approaches the value L when x approaches a, we say that L is the limiting value of f of x. Symbolically, this is written as limit of f of x as x approaches a equals to L. Now let us find the limiting value of the function 5x minus 3 when x approaches 0. That means our f of x is defined by 5x minus 3. Let's assign values to x from left and also right of 0. Now, from the left, it means you have values that are less than the limit, which is 0. So you will be having values like minus 0.1, minus 0.01, and minus 0.001, and so on. Now, this is your function, f of x equals to 5x minus 3. When x takes the value of minus 0.1, the value of your function is minus 3.5. When x takes the value of minus 0.01, the value of f of x is minus 3.05. And when x takes the value of minus 0.001, the value of f of x is minus 3.005. If we observe the first table here, you will notice that as the value of x is approaching or becoming closer to 0, the values of your function, which is f of x equals to 5x minus 3 is approaching minus 3. It's becoming closer and closer to minus 3. So that is when we take values from the left of our limit, which is 0. From the right, here we are considering values that are closer to 0 but greater than it slightly. So we have 0.1, 0.01, 001, and 0.001. If you substitute the values of x in the function, you have f of x equals to minus 2.5, minus 2.95, and minus 2.995. So from the second table also, you observe that the value of your f of x is approaching minus 3. It's becoming closer and closer to minus 3. Therefore, we conclude that from the above, it is clear that the limit of f of x minus 3 as x approaches 0 is equals to minus 3. And we write it this way: limit of the function f of x minus 3 as x approaches 0 is equals to minus 3. So we take some few examples to illustrate the concept of limit. This example says, find the limit of each of the following. A, f of x equals to 2x squared plus 3x plus 2 as x approaches 2. B, f of x equals to x squared minus 9 divided by x minus 3 as x approaches 3. And C, find limit limit of the function 5 raised to power x plus 1 plus 7 raised to power x plus 1 divided by 5 raised to power x minus 7 raised to power x as x approaches infinity, positive infinity. Solution. For A, limit of 2x raised to power 2 plus 3x plus 2 as x approaches the value of 2 is the same as limit as x approaches 2 of 2x squared plus limit as x approaches 2 of 3x plus limit as x approaches 2 of the constant 2. Why we divided it this way is that limit of sum is sum of limits. So if you have a function that is a sum of different functions that can stand on their own, you are allowed to take their individual limits, and then at the end of the day you add all the limits. And that is why instead of taking the value at the limit of this function as a whole, we can take the limit of 2x squared as a function on its own. We can also take the limit of 3x, and we can also take the limit of the number 2 as x approaches the value of 2. So this limit is the same as this plus this plus this. Now this is equals to, if x approaches to the limit of 2x squared is 2 times 2 raised to power 2 plus the limit of 3x as x approaches 2 is 3 times 2, and the limit of the constant 2 as x approaches 2 is just 2, since you don't have x there. So if you evaluate 2 raised to power 2 is 4, multiplying it by 2 you get 8. 3 times 2 will give you 6, and then plus 2. When you add these three numbers, you will have what? 16. Therefore, the limit of this function 2x squared plus 3x plus 2 as x approaches the value of 2 is equals to 16. For B, f of x is given as x squared minus 9 all over x minus 3. Now, under the concept of limit, if you make a direct substitution and it is giving you an undefined quantity, that is 0 over 0 or infinity over infinity, it is not allowed. So you have to rewrite the function in another form and try the substitution to see that it gives you something that is defined. So this particular function, if you make a direct substitution of x to be equals to 3, you will discover that the numerator will give you 0 and the denominator will also give you 0. So for that reason, we are going to factorize the numerator and then see how we can reduce the function before making our substitution. So this limit will be equals to the limit of, if you factorize x squared minus 3 using the difference of two squares, you will have x plus 3 times x minus 3 dividing x minus 3. So therefore x minus 3 will cancel with x minus 3 and you are left with x plus 3. Therefore this will be equals to the limit as x goes to 3 of x plus 3. And when you make your substitution, you are going to have 3 plus 3, which is equals to 6. Therefore, we say that the limit of this function x squared minus 9 divided by x minus 3 as x approaches the value of 3 is equals to 6. Next, the limit of 5 raised to power x plus 1 plus 7 raised to power x plus 1 divided by 5 raised to power x minus 7 raised to power x. When you look at this, as x approaches infinity, if x approaches infinity, similarly, if we make the direct substitution, we are going to have infinity over infinity. So we have to make some rearrangement and then perform some operations that will reduce the function so that we can now substitute and have something meaningful. Therefore, if you factorize 5 from the first term in the numerator, you will have 5 multiplying 5 raised to power x, and then you also have plus 7 multiplying 7 raised to power x, all divided by 5 raised to power x minus 7 raised to power x. In the next step, we are going to divide both the numerator and the denominator by 7 raised to power x. So 5 times 5 raised to power x divided by 7 raised to power x plus 7 times 7 raised to power x divided by 7 raised to power x all over 5 raised to power x divided by 7 raised to power x minus 7 raised to power x divided by 7 raised to power x. Now, if you simplify this, 7 raised to power x divided by 7 raised to power x will be 1. So you have 5 times 5 raised to power, over 7 raised to power x plus 7. And then the denominator will now be 5 all over 7 raised to power x minus 1, because this is also 1. 7 raised to power x divided by 7 raised to power x is 1. Now, when you now make your substitution, the fraction 5 all over 7 as x goes to infinity or approaches infinity, this will give you 0, because it is less than 1. So as x approaches infinity, the value will become smaller and smaller and it will approach 0. So the limit is 0, and also this one will approach 0. So at the end of the day, you are going to have the numerator as 0 plus 7 all over 0 minus 1, and when you simplify, the final answer will now become minus 7. Finally, D, the limit of the function 2x minus 1 times x plus 4 times x minus 2 all over x raised to the power of 3 as x approaches infinity. The same thing is applicable here. If you make a direct substitution, you are going to get an undefined quantity. So the first thing we are going to do is to expand the three brackets, and that means we are multiplying the first bracket by the second one and also the third one. By the time you do that, you are going to have the numerator as 2x raised to the power of 3 plus 3x squared minus 18x plus 8 all over x raised to the power of 3. So when you take the limit as x approaches infinity, then before you do that, you are going to also divide both the numerator and the denominator by x raised to the power of 3. When you do that, the numerator will now be 2 plus 3 over x minus 18 all over x squared plus 8 all over x raised to power 3, all divided by 1, because x raised to power 3 divided by x raised to power 3 is 1. So when you have this and you now allow your x to approach infinity, 3 divided by infinity will give you a 0. The same thing with the second, the third term and the fourth term here. So the only term that will not be 0 is 2. And then when you take the limit of 1 as x goes to infinity, is also 1. So you are going to have 2 over 1, which is equals to 2. So the limit of this function as x goes to infinity is 2. That's the final answer. Now, next we are going to be talking about left and right hand limit, considering x approaching a such that x takes only those values which are less than a and very close to a. Then we say x approaches a from the left, and we write it as x goes to a superscript negative sign. So when you see this, you know that you are talking about left hand limit. Similarly, if x takes the values which are greater than a and very close to a, then we say x is approaching a from the right, and we write it as x approaches a raised to power positive sign, or superscript positive sign. Note that if we let f of x be a function, then x lying between alpha and alpha plus delta, it means that the limit of f of x as x approaches alpha raised to power positive sign is equals to L. This is what we mean by right hand side limit. And when you have your x lying between minus alpha and minus alpha plus delta, then it means the limit as x approaches alpha from the from the left, f of x equals to L, implies this is a left hand side limit. We should remember that left and right hand limit are especially used when a, the function under consideration, involves what? Modulus. Another name for modulus is absolute value. The function is b, the function is defined by more than one rule. So you are going to be using left and right hand side limit when you have these two things. That is, when you are considering a function with the modulus sign or absolute value sign, or if the function is defined using more than one rule. Example: find limit of absolute value of x divided by x as x approaches 0. The solution: limit of the absolute value of x divided by x as x approaches 0 from the right is equals to limit of x all over x as x approaches 0 from the right, which is equals to 1. That means if x is approaching 0 from the right, the absolute value of x is what? X. So we have x over x, which is equals to 1. So if you take the limit of that as x approaches 0 from the right, you are going to have your limit as what? 1. Also, when you take the limit of absolute value of x divided by x as x approaches 0 from the left, which is equals to limit as x approaches 0 from the left of minus x divided by x. So if x is approaching 0 from the left, the absolute value of x is equals to minus x. So when you divide minus x by x, you have minus 1. And when you take the limit as x tends to 0 from the left, you are going to have minus 1. Therefore, the right hand limit is not the same as the left hand limit. And so we conclude that the limit of this function does not exist. For limit to exist, the left hand limit and right hand limit must be equal. And for this one, the right hand limit and the left hand limit are not equal. So therefore our conclusion is that the limit does not exist, because if limit exists for a particular function, the limit must be unique. That means it must be 1. The next example is, we want to find limit of the function absolute value of x minus 1 divided by x raised to power 2 minus 1. The solution is as follows. Limit when x approaches 1 from the right of absolute value of x minus 1 divided by x squared minus 1 is equals to limit of x minus 1 divided by x squared minus 1 as x approaches 1 from the right, which is equals to 1 divided by x plus 1. For you to get this, you have to factorize the denominator. This is the difference of 2 square. X squared minus 1 is the same as x squared minus 1 square. So if you factorize it, you are going to have x plus 1 multiplying x minus 1, and the x minus 1 will cancel the 1 on the numerator, and that is where you are going to have 1 all over x plus 1. So if you now substitute the value of x as 1, the final answer you are going to get is 1 over 2, because the denominator here will be 1 plus 1, so you have 1 all over 2 as x approaches 1 from the right. So the limit will be 1 over 2. Next, limit as x approaches 1 from the left of absolute value of x minus 1 divided by x squared minus 1 is equals to limit of minus x minus 1 dividing x squared minus 1 as x approaches 1 from the left. The same thing here, you factorize the denominator and one of the bracket will cancel with this to leave you with minus 1 all over x plus 1. And after the substitution of x as 1, you are going to have minus 1 all over 2. Therefore, the limit of the function as x approaches 1 from the left is minus 1 all over 2. Now, if you compare the two, you can now see that they are not the same. That means limit of this function when x approaches 1 from the right is not the same as limit of the same function as x approaches 1 from the left. Therefore, the limit of the function does not exist, as we earlier mentioned. Next is L'Hopital's rule on limits. Now, as I said, in limits, we don't want our limit to assume an undefined function. So this is L'Hopital's rule on limits help us to find the limit of functions that initially, if you make direct substitution, you are likely going to have undefined quantities. So the rule here says if you have such function, you can differentiate the function, both the numerator and the denominator, and then apply the limits. And in so doing, you will find that you are going to have a function that is defined, or a value, a defined value as your limit, not an undefined quantity. So the rule states that if limit of f of x as x approaches c, the Hopstall rule states that for functions f of x and g of x which are differentiable on an open interval I, except possibly at a point c contained in that interval I, if you have the limit of f of x as x approaches c equals to the limit of g of x as x approaches c equals to 0, or plus or minus infinity, where your g of x is not equals to 0, for all x in the interval I with x not equals to c, and limit as x approaches c of f of x divided by g of x exists, then the rule allows you to, if you are looking for limit of f of x all over g of x as x approaches c, is the same as taking the limit of f prime of x over g prime of x as x approaches c. That means instead of taking the limit of the original rational function, we are going to take the limit of their derivative. And by extension, this rule can be extended if the first derivative is also giving us an undefined quantity or function. We will differentiate for the second time and so on. So that is the idea about L'Hopital's rule. Example: find limit as x approaches 1 of x raised to power 3 plus x raised to power 2 minus x minus 1, all divided by x raised to power 2 plus 2x minus 3. Solution: by direct substitution of x equals to 1 into your f of x all over g of x. Here we are assuming that the numerator is our f of x, because you can see that it is a polynomial in x and it can stand as a function on its own as f of x. And we are also calling the denominator g of x because it is a polynomial in x and can as well stand on its own as a function of x. So when you make a direct substitution of x equals to 1, since your x is approaching 1, you will have this undefined quantity 0 over 0. And earlier on we mentioned that this quantity is not allowed. It's not something that we want to happen. So which is what? An undefined quantity. Now we apply the L'Hopital's rule here by differentiating the numerator as well as the denominator before we make our substitution. So therefore, limit of this function as x approaches 0 will now be equals to the limit of 3x squared plus 2x minus 1. And if you look at the numerator here, is the derivative of the numerator that is here. If you differentiate x cubed, you will have 3x squared. When you differentiate x squared, you will have 2x. You differentiate x, you have minus 1. Minus 1 here is a constant, so its derivative is 0. That's why it is not appearing here. Then the denominator of the original function is this, and when you differentiate the first time, you have 2x. The second time gives you 2. The third one being a constant, the derivative is 0, so it's no longer here. And so this is the limit of the derivative of f over the derivative of g as x approaches 1. So when you substitute now, you are going to have 3 plus 2 minus 1 all over 2 plus 2, which is equal to 4 divided by 4, and the final answer will be 1. So with the help of L'Hopital's rule, you can see that we are able to find the limit of this function instead of when you make a direct substitution giving you an undefined quantity. Next, we want to determine the limit of sine x minus sine x divided by x raised to the power of 3 as x approaches 0. Similarly, if you take if you substitute directly into the function given, you will notice that you are going to have 0 all over 0. So that means we have to differentiate and before we substitute. Now when you differentiate sine x, you are going to have cos x. When you differentiate sine x, you will also have cos x. So the derivative of the numerator here is what you have here as cos x minus cos x. The derivative of x cubed is 3x squared. And so if you now substitute your limit as x goes to 0 or approaches 0, you are still going to have 0 all over 0. Okay, so you have to, as I said earlier on, apply L'Hopital rule the second time. You keep on applying it until it gives you something that is meaningful. So applying it for the second time, you differentiate cos again, you have sine x. You differentiate cos x, you have minus sine x, and this will now make it what? Plus sine x. Then if you differentiate the function as at the denominator, it will give you a 6x. Still, if you apply the limit, you are going to have 0 all over 0. So you apply L'Hopital's rule this time around for the third time. So differentiating sine again, sine x, you have cos x, sine x, you have cos x, and then differentiating 6x as a function will give you what? 6. Now when you take the limit of this as x approaches 0, you are going to have the limit as x goes to 0 of cos x is 1. The limit as x goes to 0 of cos x is also 1. So you have 1 plus 1 as the numerator. The denominator is a constant, so taking its limit as x approaches 0 will still leave you with that constant. So at the end of the day, you have 2 divided by 6, which will finally give you 1 over 3 as the final answer. So therefore, the limit as x approaches 0 of this function sine x minus sine x all over x raised to power 3 is 1 over 3. But before you arrive here, you must have applied L'Hopital's rule 3 times. Okay, that means you differentiate the function, both the numerator and the denominator, 3 times before you arrive at the final answer. So that tells us that L'Hopital's rule can be applied a number of times, sometimes before arriving at our final answer. Now the next thing we'll look at is continuous function. From a layman point of view, a continuous function is one which has no break in its curve and it can be drawn without lifting the pencil from the paper. A function f of x is continuous at a point x equals to a if 1. F of a exists. 2. Limit as x approaches a of f of x exists. 3. F of x equals limit of f of x as x approaches a. All polynomial functions are continuous, as are all rational functions, except undefined, that is where their denominators are equal to 0. So these are the conditions that must be satisfied before we can say that a function f of x is continuous at a point x. So next example, we want to show that the function f of x equals to x minus 3 divided by x squared minus 9 is continuous at the point x equals to 3. Solution. Here we need to show that the following conditions are satisfied: that f of 3 and limit of f of x as s approaches 3 exists. Then also we need to show that f of 3 is equals to the limit of f of x as x approaches 3. Now A, f of 3, when you make direct substitution, is going to give you 0 all over 0, which is what? Undefined. B, limit as x approaches 3 of x minus 3 all over x squared minus 9 is equals to x minus 3 divided by x minus 3 times x plus 3 when you factorize the denominator of your original function, which is x squared minus 9, using the difference of 2 squared. So the limit as x approaches 3 of x minus 3 all over x minus 3 all over, times x plus 3. This will cancel with what? The x minus 3 at the denominator, and you are left with 1 all over x plus 3. And when you make your substitution, you are going to have 1 all over 6. Now C, you will now discover that f of 3 is not the same as the limit of f of x as x approaches 3. So conditions A and B are not satisfied. Therefore, the function f of x is not continuous when your x is taking the value of 3. So the next thing is limit and continuity of function, which the exercises under this, which are given for students to try and find whether the function is, the limits exist, and you try to find them. So this exercise says evaluate the following limits. A, limit as h approaches 0 of the square root of 4 minus h minus 2 all over h. B, limit of root of x all over x plus 1 as x approaches 1, and so on and so forth. Thank you for listening. So this is the end of this segment. As I said, other segment will follow from my colleagues who are taking this same course with me. Thank you very much.